So in this math, we'll design a beam, and that has to be a W section. We have external loading, 0.2 kip per feet for dead load, and 0.8 kip per feet as a live load, and it has a simply supported beam, and you have no lateral movement. So it is laterally supported beam. Now you can use different grades of steel. For this math, I will use A36 steel, and approach would be ASC method. So the first thing first that you need to understand the moment that is actually coming on the structure at a critical position, that is at the middle of the beam. That's the most critical point. So we'll find out the moment that is coming on the structure. So the moment that is coming on the structure would be, let's call that actual moment. We have a load of point 0.2 and you have a load of point 0.8. Since it's AST method, it will be just a summation. That would be like W L squared, and since it's like simple span, so it will be the formula. So you have a W value of zero point 0.2 plus zero point 0.8, that would be 1 kip per feet, and you have a length of 20, so it would be just a 20 squared, and you just divide it with 8, so you get a value of how much. You get a value of 50 kip feet. Now you need to design the section. So the thing is that you have several formulas to calculate the moment you will get for a particular section. Uh, you have a moment equation, which is this: mp is equal to fy multiplied by zx, and zx is we call that something, I don't know right now. You have another equation to find out the moment, which is this. You have another equation to find out the moment, this. We call ZX plastic section modulus, if I'm not wrong. Well, you can use this formula, MP is equal to FYZX, if your slenderness ratio, we call that slenderness ratio, lambda is equals to BF over 2TF. Here BF is width of flange and TF is thickness of flange. So if your slenderness value is less than this quantity, which is 0.32 root over E over Fy, or you just plug the value of E, which is 29,000 ksi, you will eventually get this term, which is 65 over root over Fy, and you have to keep Fy in ksi. So we'll assume that our slenderness value is less than lambda pf. We call that slenderness value of flange at plastic capacity. Well, so first of all, we'll assume that we are in plastic range, or our flange is compact flange. These two terms are uh, similar. If your flange is compact, you'll get the moment that is plastic moment, or you are in the plastic range. We call this as plastic range. So for that, you have an equation of mp is equal to fy zx. So we'll find out that our again, yeah, this is the actual moment, but for the design purpose using AST method, you need to find out the nominal moment that you need. For that, you have a multiplying factor, which have a value of 1.67, and it will be multiplied with 15, and you will get a value of 83.5. If that is the thing, you now can find the value of zx. Zx will be the value, that is the moment, divided by fy. Since the zx is equals to, sorry, plastic moment is equals to Fy Zx. So from that we can say that Zx will be equals to the moment. We are assuming that Mn will reach empty plastic moment. So your moment you have is 83.5. We'll convert it in terms of inch because Fy is in KSI and we are using A36. So for that you have a value of 36. So from there you will get a value of Zx as 27.8. It has a unit of cubic inch. So using the value of Zx, we will select the section. So our Zx value is 27.8. So you have uh, around x-axis, you have a z value in this column. So we need a value of 27.8 or above it. So for that, we can select this one, which is 29.3. Since it is just above 27.8, for that you have a section of W1222, and for that we need a few parameters, that is width of flange, which is 4.03 or 4, whatever, quite close, and thickness, which is 0.425. So these two parameters we need uh, to calculate further. Well, the thing we're getting from this structure, that is our zx value is our section is W1222. So for that we have a zx value of 29.3 cubic inch. We have a few other parameters that are uh, flange width as 4.03 inch and thickness of flange as 0.425 inch. So from there we'll find out the value of lambda, slenderness ratio. So the formula is 2, sorry, BF over 2 TF. Here BF is 4.03 and TF is 0.425. From there you can find out the slenderness ratio, and that would be a value of 4.7. So this value have to be less than or equal to 65 root over Fy, and this value generates 10.83. So the thing, we assume that we are designing a section that is compact or that will limit uh, that will reach plastic limit, and the moment we will get as plastic moment. So our assumption was okay. Now we'll find out the moment that we will get for the section we are getting. So the moment we are getting is Fy, that was 36, and the Zx value, which is 29.3. So from there you'll get a value of 154.8 cube inch or 87.9 cube feet. Cube feet. And the allowable moment will be 87.9 divided by 1.67, because 1.67 is reduction uh, factor or whatever, and the value you'll be getting 52.63 keep fit. Now the section has a unit weight that is 22 pound per feet. We'll check that. Yeah, if we consider the self weight as 22 pound per feet, will that be satisfying? So the moment including sorry including self weight will be, we had a previous moment of 1 and we now have a 22 pound per feet. So if we convert it in cube feet, so that would be 0.22, and we have a length of 20. So square it and divide it by 8. So you'll get a moment of 51.1 cube feet, which is less than our allowable moment. So we can say that the design section MW22 is working to withstand the external loading on the structure.